So I want to talk about homogeneous coordinates because I think they are one of the most powerful methods of understanding modern geometry. So they're not as well known as they should be, but as opposed to Cartesian coordinates, if you use homogeneous coordinates, then it helps to understand the sort of plane in its entirety, that is, with the sort of points at infinity included. This is a lot more appropriate, for example, in projective geometry. And one of the consequences of using homogeneous coordinates is that it's much easier to see the sort of duality between points and lines. It's much easier to prove all the theorems of projective geometry. In fact, rather than the synthetic approach, where one has to assume quite a lot of axioms, maybe 9 or 10 axioms, to do projective geometry on the plane, working with homogeneous coordinates, we start with some really simple definitions of points and lines and when a point touches a line. And from there, we pretty much get the whole of projective geometry for free. Moreover, we can think about different kinds of number systems, like real number systems or complex ones, to get lots of different sort of varieties of geometry, and we can study them all simultaneously. So I really think it's a fantastic tool for studying geometry. It's also pretty easy, to be honest. It's pretty simple once you get your head around the subtleties of having different ways to refer to one particular point. So what are homogeneous coordinates? Well, a nice way to start thinking of them is homogeneous coordinates are a way to refer to a point in the plane, and we do so with three numbers, x1, x2 and x3. Now the critical thing here is that to describe a specific point, the only thing that's important is the ratio between these three numbers, x1, x2 and x3. And so in homogeneous coordinates we have this special property that we can multiply the coordinates of a point by any non-zero constant, and we get a new expression, but that is equivalent to the old expression. It refers to the same point. So all that matters is the ratio between x1, x2 and x3. So x1, x2, x3 refers to the same point as 2x1, 2x2, 2x3, and so on. So to be honest, we can really start there and very quickly start to build up geometry just from this idea. We don't even have to attach a geometric interpretation to these things yet. We just get all of geometry sort of algebraically, if we like. However, of course, you will want to think about some geometric interpretations. So let's have a look at one of those. Well, I've pictured one of those here. I'll talk about that in a moment. I just want to say one thing. It's very important. We don't allow x1, x2 and x3 to all simultaneously be 0. So we never allow that. That doesn't really correspond to a point in the plane in the usual sense. But anything else is fine, and we're free to multiply by any non-zero number. Now, today we can probably think mostly in terms of x1, x2 and x3 being reals, or rationals if you prefer to work over the rational numbers. But you should bear in mind that actually we can choose these things to be elements from any commutative field. So we could have these as complex numbers, for example. And we'll see later that when we do so, we get some very interesting insights into the natures of conics, which of course are a very nice thing to use projective geometry to study. And homogeneous coordinates are a very nice thing to use to study projective geometry. So it's all matching up quite nicely. Anyway, what's a geometric interpretation of these homogeneous coordinates? How can we visualize one of these points? Well, there is a connection with Cartesian coordinates, which I shall go into in a moment. But another way of thinking of things is in sort of barycentric coordinates. So we're going to have these three special points with homogeneous coordinates 1, 0, 0, 0, 1, 0 and 0, 0, 1. for this moment, don't worry too much about where these points are in the plane. Suffice to say, they form a triangle. In other words, they're not all along the same line. Okay? Now, we can interpret this point x1, x2, x3 as the centre of mass that you'd get if you load a mass of x1 onto this vertex here, a mass of x2 onto this vertex here, and a mass of x3 onto this vertex here. And from this interpretation, you can hopefully see that all that really matters with regard to what point we're referring to is the ratios of these three numbers. So if we load twice as much mass onto each vertex, it's not going to affect the position of the centre of gravity that we're going to get. So this is of course an interpretation that makes a lot of sense if we're considering x1, x2, x3 to be positive real numbers. And that's the normal way we're going to think about this for this lecture. So here's one interpretation. It's just to give you a bit of physical insight into what these things mean. We're also going to look at some connections with Cartesian coordinates, but I just want to again emphasise that really we can just think of this thing as a purely algebraic thing starting from here, and we'll very quickly see a lot of geometry emerging from this idea. Okay, so as I've already said, we can just pick up and run with homogeneous coordinates as an object in their own right, but I feel like it might help you if you've not seen these things before to talk about some connections with Cartesian coordinates, which you probably have seen before. So just to recall, in Cartesian coordinates we describe points of the plane using two numbers. So we have a special point called the origin, 0, 0 here, and any point on the plane is described by a pair xy, where x is the number of units to the right of the origin that point is, and y is the number of units up from the origin that point is. So in Cartesian coordinates we just need two numbers to describe a point, and every point on the plane has a unique description in terms of these coordinates, except perhaps the points at infinity, if you want to believe in those or whatever. So homogeneous coordinates then are a bit different, but there is a very natural connection between these two things. So in particular, let's say you have a point xy in the Euclidean plane as described by Cartesian coordinates. Well, how do you describe what that point is in terms of homogeneous coordinates? Well, it turns out that it's a very simple job actually. All you have to do is just append a 1 at the end of the description of a point. So the point xy in the Cartesian coordinate system becomes the point xy1 in the homogeneous coordinate system. Now, these being homogeneous coordinates, all that really matters is the ratio between these three numbers. So we're free to multiply them by any non-zero term, and we still get a description of the same points. So xy1 is equal to 2x2y2, and so on. So that's how you go from Cartesian coordinates to homogeneous coordinates. So we see that homogeneous coordinates in a way are at least as descriptive as Cartesian ones. Now how do we go back again? Well, by looking at how we go from homogeneous coordinates to Cartesian coordinates, we start to get a sense of why homogeneous coordinates can be more useful. So in particular, if x3 is not equal to 0, then, and we have homogeneous coordinates x1, x2, x3, then what we can do is multiply all of these entries by 1 over x3, and then we'll get x1 divided by x3, x2 divided by x3, and 1. And that operation is just multiplying all of the entries by a non-zero constant. So that doesn't affect the point which we're talking about, and it converts the coordinates essentially into this form. And then we can see by this sort of relationship that we can go from here to here. And so x1, x2, x3, that's equivalent to writing it's hard to write at this angle. Okay, so those two things there are equivalent. And then we can easily see from this relationship that we can go from here to here. And so this is a description of this point here in homogeneous coordinates written in Cartesian coordinates. So then we can see why homogeneous coordinates are in a sense more powerful, because of course we can do this kind of conversion when x3 is not 0. But what about when x3 is 0? What kind of points are we referring to with homogeneous coordinates which have the last entry equal to 0? Well, in that case, essentially, you might say that we're referring to points at infinity on the Cartesian plane. And to get a sort of vague sense of what I'm talking about, consider these quantities. Well, when x3 is equal to 0, we are dividing a number by 0. Of course, I mean, we wouldn't technically be able to use this argument because you're not supposed to be able to divide numbers by 0. But you can see that when you're dividing a number by an increasingly small number, the result gets larger and larger. And so in some sense you can see that there are infinities appearing in this expression when x3 is 0. Now, the beauty of homogeneous coordinates is that simply by imagining that when x3 is 0, we have points at infinity, we can then talk about these things in a very concrete way. And in fact, we don't need to worry too much about the interpretation of that, because as you shall see, the coordinate system works in its own right, and in a way we can think of it as a fundamental object. So the real power of homogeneous coordinates is that in addition to allowing non-zero third entries here, we can also allow 0 third entries. Now, of course, such points with such homogeneous coordinates can't be given exactly the same kind of interpretation via Cartesian coordinates, because such things would involve division by 0. However, it turns out that such points can still be interpreted geometrically. It's just that they are sort of points which are on the kind of line at infinity, which we can think of in some sense as surrounding the standard Euclidean plane. And when we think about projective geometry, we can imagine augmenting the Euclidean plane by this sort of set of points at infinity. And the homogeneous coordinates give us a way to think about and include such points and do analytic geometry involving them. And in doing so, by adding these points, we sort of complete the system, and then we're able to see more clearly this kind of duality which happens between points and lines. So we can see our sort of point-line duality working algebraically. By point-line duality, I mean this projective geometry idea that points and lines essentially are objects which have kind of equal standing in the geometry of the plane. And you can see this very directly when you work with homogeneous coordinates, which can also be used to describe lines. So I'll carry on, let me explain how that works. So one of the reasons I like homogeneous coordinates so much is that you need so little foundation in order to be able to quickly get to a great deal of the results from projective geometry. So unlike the sort of standard synthetic approach, which I've talked about in previous videos on foundations of projective geometry, where you need lots of axioms and assumptions to begin, in projective geometry you pretty much just need the idea of the coordinate system, the definitions of points and lines, and the definition of when a point lies upon a line. And from there you can quite quickly go and prove lots of the important results of geometry. And so this is the most important sort of picture that I'll talk about in these lectures, because it gives you the definition of a point, the definition of a line, and the condition for when a point lies upon a line, or when it's touching it. So let's have a look at this. A point, we typically use lowercase letters for points now when we're dealing algebraically, and surround them by round brackets. And a point is just given by a triple x1, x2, x3, lowercase letters. A line is also specified by homogeneous coordinates, 3 entries. We're using capital letters for this. Capital X1, capital X2, capital X3 are the 3 different components of a line. You'll understand the interpretation of this later on when I go through some examples, I hope. But the condition for a point to be on a line is when this is 0. So when little x1 times big x1 plus little x2 times big x2 plus little x3 times big x3 is equal to 0. And we give a kind of shorthand for this using these triangular brackets. And you'll probably recognise this as the dot product, or sometimes called the inner product of these 2 vectors. And so the important thing here is that both of these point and line are described in very similar ways in terms of 3 numbers. We do not allow each of these entries, x1, x2 and x3, to all be 0 simultaneously. We don't allow these big x1, x2, x3 to all be 0 simultaneously. Those cases are they don't have a geometric interpretation essentially, but anything else is fine. And we're only interested when we talk about a point if we multiply all these 3 numbers by any non-zero constant, such as rho. We get a new expression, but we think of it as referring to the same point again. Similarly, we can multiply all of these capital X entries by the same non-zero constant, and we get a new expression, but we take it as referring to the same old line. Now, essentially, this means that points and lines are treated equivalently, and you can see that they have a completely symmetric role in the way that they interact with each other when we're talking about a point lying upon a line. So it might be better perhaps to use some kind of symmetric terminology, like when a point touches a line, since really these 2 objects are on equal footing in our kind of system. So I'll just say this again, just because it's perhaps the most important part of the lecture. A point is described by 3 numbers. We use round brackets to denote a point and lowercase letters. A line is also described by 3 numbers. We use square brackets to denote a line and capital letters. And all that matters is the ratio between these 3 numbers when we're talking about the points, similarly with the line, and we don't allow all of these 3 entries to simultaneously be 0, and we don't allow this kind of going on here either. And this is the condition for when a line and a point meet, essentially when the inner product of their vectors equals 0. Okay, so just to say a little something about shorthand, I might sometimes write this kind of term like this. So sometimes it can be kind of clunky to keep putting these round brackets around the points and the square brackets around the lines. So sometimes I might just miss them out and, for example, express this product like this, because it'll often be clear whether I'm talking about points or lines just by the kind of case of letter which I'm writing. What does this way of referring to lines mean? I mean, here we have a line 3 minus 2, 2. There are its coordinates. So how can we think about this? Well, essentially we can think of what it means in terms of an equation, in terms of this equation here, which is the equation for when a point is on a line. So we can interpret this line, 3, 2 minus 2. We could also say it's the line 6, 4 minus 4, or any non-zero multiple of these three numbers. Anyway, we can interpret it as an equation like this, specifying all the homogeneous coordinates of points which are on this line. So a point little x is going to be upon this line, big X, when 3 times x1 plus 2 times x2 minus 2 times x3 equals 0. So this is the equation which essentially describes all the points which are on this line. Now, how do we interpret this equation? Well, essentially the equation gives us lots of values x1, x2, x3, which give us homogeneous coordinates of points upon that line. So what we can do, we know that when x3 is equal to 1, essentially then x1 and x2 can be interpreted as in terms of Cartesian coordinates, as I was saying at the beginning. So I'd just like to, just for a minute, just venture back into the realm of Cartesian coordinates so we can think about this line in a more familiar way. I don't want to have to keep going back to Cartesian coordinates. Hopefully we can move past that, but let's just go there for a moment to get some familiarity with this. So we can set x3 is equal to 1, and then we're basically considering all the different points of this line which are sort of finite, and then we're free to think of x1 in terms of a sort of Cartesian x. I'm using a curly x now, so don't get too confused. And similarly, a curly y is now represented by x2. And so we can see that this has the Cartesian equation 3x plus 2y minus 2 equals 0. We can rewrite this in the usual way, so we have y is equal to 1 minus 3 over 2x. And we can draw this equation. So essentially what this is the sort of equation of the finite, of what's going on with this line for all the points except the infinite. This is in a sense a more general equation, this one with the homogeneous coordinates, because we can also think about what happens here when x3 is equal to 0. Essentially then this is telling us about what the about where this line meets the line at infinity, and what the little x coordinates are for the point where that happens. Okay then, so just as if we're given a line, we can interpret that as an equation of points. So in an exactly dual way, if we're given a point, we can interpret that as an equation which gives all the lines which go through that point. So, for example, if we have the point 2, 3, 6, then we get this equation here in terms of lines capital X, the equation 2x1 2x1 plus 3x2 plus 6x3, which gives the homogeneous coordinates of all the lines capital X which pass through this point here. And so it's interesting to see this kind of duality, and I think it's also quite revealing about how we tend to think of objects in the world. So since we can have an equation, I mean, it's natural for us, I think, if we have a line, to interpret that as an equation of points upon that line. We tend to think better in terms of points. Whereas if we have a point, it's much less natural for us to then think of an equation of lines through that point and to get a sort of expression for the coordinates of all of those lines. But we see that kind of logically they're both equivalent ways of looking at things. We can also think, for example, about all the lines capital X through the points 1, 0, 0. That's obviously a special type of point. Those are all the lines which have an equation capital X1 equals 0. And by sort of continuing this reasoning, we can then think about this sort of reference triangle. So we have these three special points, 1, 0, 0, 0, 1, 0 and 0, 0, 1. And they're special points in our homogeneous coordinate system. Now it turns out that essentially when we're doing theorems in projective geometry, we can really pick any three non-collinear points to serve as these 3 points of our reference triangle. Because essentially whatever 3 points we pick, we can always find a sort of projection to transform them any way we see fit. So, I mean, we could think of these as having special interpretations in terms of Cartesian coordinates, which are somewhat elegant, and I won't bother going into them. But suffice to say, we have these 3 special points, and then you can see by what I've written so far that this reference triangle also has these 3 special edges. 0, 1, 0, joining 1, 0, 0 points 1, 0, 0 to 0, 0, 1. Line 1, 0, 0, joining points 0, 1, 0 to 0, 0, 1, and so on. And you can check for yourself that these lines written in blue do indeed join the points drawn in green, as I've shown. So we can think of a reference triangle in terms of points, or dually a reference triangle in terms of lines. So this duality principle is going to be true for pretty much everything I talk about. You can always convert things so that we're talking about points instead of lines. And there's basically an equivalent notion of everything under this kind of dual flip. So for example, we could say that 3 points are collinear. That means 3 points lie on the same line. The kind of dual statement of that would be that 3 lines are concurrent. That means 3 lines go through the same point. And you can see that basically you can get this kind of dual expression by getting the algebra and replacing the little x's with big x's and the round brackets with square brackets and so on. Now, an interesting question, something for you to think about. If you have a point with particular coordinates, say 2, 3, 6, then what does the line look like that has the same coordinates, and how is it related to the point? I'm not going to go into this yet, but there's a very nice answer to this question, which has to do with polarities. Well, I'll say quickly, but I'm not going to go into detail yet. Essentially, to do such a conversion from a point to a line, you find the polar of that point with respect to the unit circle. And if you don't know what I mean by that, I give a link to a video in the description below that you can find out about that from. Okay, so now we're going to move forward and look at some expressions for important things, in particular when 3 points are in a line with each other, or collinear as we say. And so when are 3 points x, y and z collinear? Well, just by the definitions, they'll be collinear when there exists a line capital X such that these products here all equal 0. So the product of little x and capital X is 0, as is little y in capital X, as is little z in capital X. Okay, so we're really interested in what that condition means, and it turns out that you can, if you write all these 3 things as equations in terms of capital X1, capital X2, capital X3, the coordinates of the line capital X, and then you solve out to eliminate the capital X terms, you'll see that this expression is equivalent to this expression here, which is that the determinant, with rows x1, x2, x3, y1, y2, y3, and z1, z2, z3 is equal to 0. And if you don't remember about determinants, then don't worry, because you can just think of this expression as being equal to this one here. This is a sort of way to write out what this 3 by 3 determinant is in general. In fact, it's obtained via a special trick that you can do with 3 by 3 determinants, which is to expand them out. It's this times this times this, take away this times this times this. So essentially you're adding on diagonals like that and taking off diagonals like that. So then it's plus this times this times this, take away this times this times this, plus this times this times this, take away this times this times this. So essentially you're multiplying when you're going, I've got my hands the wrong way around, you're multiplying when you go down by diagonals like this and adding, and you multiply diagonals like this and subtract them. And you imagine that this is sort of wrapped round on a cylinder. So when you go off the left hand side, you come on the right hand side and so on. Okay, so that's one fairly useful expression for when 3 points are collinear. Now let's have another look at this. Let's just, if we use some different notation, so rather than calling this point capital X1, capital X2, capital X3, sorry, this line, rather than calling it capital X1, capital X2, capital X3 in square brackets, we can instead call its components lambda, mu and nu. So those can be new ways to write x1, x2, x3. There's no real advantage to doing this apart from that it's more traditional to think of these expressions as representing parameters. So we can start to think of a parameterization of all of the points on a line. And so we basically see that this condition here, just by rewriting capital X in terms of these, with its coordinates given by these 3 numbers here, we find that this condition of collinearity is equivalent to this one, that there exists a lambda, mu and a nu that are not all 0, such that lambda xi plus mu yi plus nu zi equals 0 for each I in 1 to 3. Okay, so the advantage of this is that we can mess around with the expression to get a sort of general condition for the set of points which line up with a couple of distinct points. So let's say we have a pair of points y and z. So in this case, a general point that's in line with these things, well, provided that y and z are distinct, if we take a look at this expression here, we can see that essentially that's equivalent to the condition that lambda is not equal to 0. I mean, hopefully you can check for yourself that when lambda is equal to 0, mu and nu are proportional to each other, and therefore, x and y are proportional to each other, and therefore basically describing the same point. However, when lambda is not 0, we can essentially get an expression for x as this kind of term here. Now, when you go through the algebra of this, which I strongly suggest you do, you'll notice that I've done a bit of a trick to get to this, in the sense that I've exploited this fact that you can multiply a vector by a sort of non-zero constant and it's still referring to the same point. So this is done a lot in this kind of setup. So essentially we sort of absorb the lambda term into the mu and the nu term, and we find that a general point x, a general point z, which is collinear. I'll start again. A general point x, I was right the first time, a general point x which is collinear with y and z can be written as mu times y1, nu times z1, comma mu y2 plus nu z2, comma mu y3 plus nu z3. So we can write that in a more concise way as just being the constant mu times y plus the constant nu times z, where mu and nu are any two elements that are not both equal to 0 at the same time. So this essentially gives us a parameterization of the line. Now, it might look strange for those of you familiar with sort of the description of affine combinations of vectors, because essentially a line's a one-dimensional object, but here we're parameterizing it with two different numbers. But that's a consequence of the fact that in homogeneous coordinates there can be many expressions for a particular point, and all that really matters is the proportions of the three numbers which go into the coordinates of a point. So I strongly urge you to check these results, because I mean this is really fundamental stuff. This is the sort of definition of collinearity, and so I recommend you check out that this formula works, that this is equivalent to this condition above, and also that this sort of formula makes sense as the expression of the set of points collinear with distinct points y and z. Okay, so we have these distinct points y and z, and then we have this expression mu y plus nu z, which is essentially a parameterization of the set of points on the line through y and z. So essentially we have two parameters here, mu and nu, but we can basically reduce this. So if you think about it, any point on this line of this kind, apart from y itself, can be written like this, because provided we're not talking about the point y itself, we can express the point like this for some value of nu which is not 0, and then essentially we can just absorb this nu into the mu, divide the whole equation by mu and rewrite mu as whatever is mu divided by nu, and we can get this kind of an expression for that point on the line. So all the points apart from y can be written in this kind of form, which is nice because this is essentially just a one parameter description of a set of points on the line. And how do we get the point y back? I mean, it'd be nice to talk about all the points on the line. Well, we can, if we like, adopt the convention that when mu goes to infinity, this expression is describing point y itself. And that sort of makes sense, right? Because when mu's very, very large, this term here is going to dwarf this term here. So we can adopt this convention if we like. Now, I don't think anything I intend to say in these lectures is going to rely on this kind of convention, but it is fairly useful to bear in mind. Now, we can actually go further. So we started off with this two parameter description of the set of points on a line. Now we get to here, we've got a one parameter description. It turns out that we can describe, so say we have a couple of points, y and z, distinct points on the line with homogeneous coordinates y and z. Well, it turns out that we can actually describe any third point on this line without using any parameters at all. So, excuse me, if you take a look at this expression here, let's say we have a specific point, say x, which is of the form mu y plus z. Well, we can select we can sort of, because we're free to multiply a point by any non-zero constant, so we can essentially absorb this mu parameter inside the y parameter. So we can sort of imagine that the coordinates y1, y2 and y3 is suitably scaled so as to kind of absorb this mu parameter inside, and then we can rewrite this mu y plus z simply as y plus z. And so you can just do this once for any particular point on the line other than, this is a mistake here, that ought to be a z. Okay, so for any particular point on the line other than y and z, we can just write, that's a mistake as well, we can write that third point as y plus z. But if we have another point on the line, let's say here, of course that can't be written in the same way. So once we've got more than one point on the line, it's time to introduce the proper parameter. So essentially what we're saying here with this bottom bit is that in homogeneous coordinates we have this freedom of being able to express a particular point in lots of different ways, and we can essentially take advantage of this in order to be able to write a third point collinear with y and z as y plus z. We can suitably scale up the three numbers in the coordinates of y, so we can do that. Okay, so now we have the fairly easy job of just dualising everything that we've just talked about in terms of lines instead of points. So the dual of 3 points being collinear, 3 points lying upon the same line, is that 3 lines would be concurrent, meaning that they all pass through the same point. So if we have distinct lines with homogeneous coordinates capital X, capital Y and capital Z, then they're going to be concurrent if and only if there exists a point X which lies upon them all at the same time. So all of these products here, they're all equal to 0. And the way that this works is exactly like before. So we can find that this is equivalent to the condition that this determinant here is equal to 0. And just dualising the argument before, we can get this general expression mu y plus mu z, which is a parameterisation of the sort of pencil of lines which are concurrent with y and z. Okay, so we have a couple of lines y and z, and they're meeting at a specific point, and this is essentially a parameterization of all of these lines. And everything I've just talked about also applies to this case where we're talking about lines instead of points. So projective geometry has this complete duality, as is evident by the fact that points and lines are basically just distinguished by round brackets or square brackets. Apart from that, they're basically algebraically the same thing. And so it's fairly obvious how to dualise all these different results, and because of that I'm not going to talk about the duals of every single result. You can go through them yourself and think about the duals of these things.